Hello, I'm back. We're talking about the last section on waves. We're talking about the Doppler effect, a very interesting quality of waves as they travel throughout, the universe. Light waves, sound waves, they all have the Doppler effect. Now, if you're not familiar with the Doppler effect, we're going to be talking about it here today. Um, if you recall, waves emanate from a source, like our wave source that I have right here. This red wave source is constantly emanating light waves. Let's imagine that it's a sun or a star of some kind, and it's pumping out waves out into the universe. Of course, it's going to be pumping these waves out everywhere, not just in one direction, but for our purposes, uh, we're just going to be looking at this one wave. Boom, it's popped this one wave out and it's sending it out into outer space. Eventually it's going to reach an observer. And for the purposes of our discussion today, that observer will be represented by Dwayne the Rock Johnson. All right. So this light wave is being pumped out of this wave source here, and it flies through outer space until it reaches Dwayne. Okay. The Doppler effect starts when either the wave creator, like our wave source here, or our wave observer starts to move. If there's motion either from the wave generator or from the wave observer, the way that wave is interpreted is different. Basically, as things are moving towards or away from each other, those waves can be, the wavelength can either be stretched or compressed. And as we saw when we looked at this electromagnetic spectrum, when wavelengths get longer or shorter, that changes the way those waves are interpreted. So, for example, if we were able to take a radio wave and squeeze it enough, eventually it could become a microwave, or it could become an ultraviolet wave if we squeezed it enough, that wavelength. So, for our purposes, let's imagine that Dwayne is moving closer to that wave source. As he gets closer to it, as he's moving towards it, he's receiving these waves faster, right? Because he's moving into the waves. If he were just standing here, he would be getting hit with, let's call it one wave per second. One wave, one wave, one wave. But if he's moving towards the wave creator, towards the wave source, now all of a sudden he's getting hit with more because he's moving towards the wave creator, the wave source. So now all of a sudden he's getting hit with two waves per second. One wave, one wave, one wave, one, right? That's going to affect the way he interprets those waves. Let's say that this is a sound wave. Now all of a sudden the sound has gone from one wave per second frequency to three waves per second frequency. For a sound wave, that means that it's gone from a lower pitch sound to a higher pitch sound. So instead of, you guys are going to love this. So instead of receiving a sound and it's sounding something like, now all of a sudden, as he moves towards it, that frequency is going to get higher and higher, and so he's hearing something more like a higher pitch sound. Or if he moved even faster, I'm not going to go any further. That's the basic idea. Now, the opposite is true if the wave source and the observer are moving away from each other. So as Dwayne is standing here, let's say he's being hit with one wave per second, but how does that change if instead of moving towards it, he's now moving away from the wave source? Or if the wave source were moving away from Dwayne. Now, all of a sudden, our waves would be getting stretched. He's getting hit with fewer than one wave per second. Let's say he's getting hit with half a wave per second, or one wave every 2 seconds now. So that's going to stretch out that wavelength, and he's going to be interpreting those waves differently. So, for example, if he's looking at, let's call it a sound wave again. So currently he's getting hit with one wave per second, but if he starts to move away, the frequency of that wave goes down because he's getting hit with fewer waves per second. And so now instead of a he's getting hit with a because as he's moving away. But as soon as he stops, it's back up to that regular intake. That's the Doppler effect. It basically says that if either the wave source or the observer are moving, either moving towards each other or away from each other, that affects the way the observer receives those light waves or those waves, period. For light, that can affect the color of light that we see. And we see that when we look up into the night sky. We'll look a little bit more into this in the future. But the basic idea is that if this is a star, for example, way out in the night sky, and it's pumping out light, if that star is moving towards us, the wavelength gets squeezed, and the light that we see from that star, it gets changed because the wavelength is squeezed a little bit. Uh, the wave the wavelength gets shorter, and the light that we receive here on Earth, or Dwayne receives when he looks up into the night sky, that light now looks a little bit more blue because the light is moving towards us. That because the light source is moving towards us. If the star is moving towards the Milky Way galaxy, or it's moving towards planet Earth, then all of these waves are going to get squeezed tighter. And so when we look up there, the light is going to look more blue. We call that a blue shift. Let's type that in. If the source is moving closer, hold blue shift. Make it a separate. If the source is moving closer, a new one. Bam, boom, pow, blue. That's not right. Boom, bang, type here. Blue shift. The geniuses amongst you will probably already figure out how that's different if the source is moving away from you. If the source is moving away, I'll give you a sec to think about it. Blues Clues style. If the source is moving closer to us, the wavelength is getting smaller, and we say that the light is looking a little bit more blue. We call that a blue shift in the light. If the source is moving away, however, the wavelength is going to get longer. It's going to move further down this spectrum until eventually the light appears a little bit more red. So we would say that that is a red a a red shift. Okay, so that's the basic idea here. That if if the source is moving closer to the observer, uh, the light gets shifted towards the blue. If they're moving away from each other, the light is shifted towards the red. Okay, so when we look up in the night sky and we see a bunch of stars up there that are red, that indicates to us that most of the stuff out there is moving away from us. Okay, it's all being red shifted. Now, that doesn't mean everything's being red shifted, but some of it, in fact, a lot of it, is being red shifted away from us. As it's moving away, the light gets stretched out, and so it appears red to us as the observer. That's the Doppler effect. I'll leave you with a really good example, one of perhaps my favorite example of the Doppler effect, from a video on YouTube that is frankly the worst video quality on the entire website. It's tough. Man, is it hard to look at. But it does a great job of I hope that I have my audio turned on. Oh, if this doesn't work, I'll be very sad. Here we go. Okay, so very bad quality video. It's a fire truck running down the road. If you can't tell from all 7 of the pixels on here, it's a fire truck rolling down the road, and as it gets closer, the sound waves are being compressed together, high frequency, higher pitched. But as soon as it passes the observer and starts moving away from us, now all of a sudden those waves are getting stretched out, and so the pitch of the frequency of the sound and the pitch goes way down. So let's listen to it. It's approaching, getting louder, high pitched, but as soon as it passes us, you can hear the sound waves. Now they're stretched out. The frequency is way lower. And so it's moving away from us. That's the Doppler effect. As it moves away, those waves are now getting stretched out. We have a longer wavelength. Uh, and that's exactly how redshift and blue shift works. As we're moving closer, frequency goes up, either a higher pitch if it's sound or more blue if it's light. And now that the truck is moving away or the star is moving away, we have a longer wavelength, less frequency, a red shift, or a downward pitch. Great. That's the Doppler effect. Next time, oh, you know what? We've got time. Let's look at some redshift stars here. Uh, Maybe we can find some in that Andromeda picture, actually. Zoomable image. You guys know my favorite picture ever. Let's zoom way in. Okay, so a lot of these stars are reddish. You'll see that it's a little orange, a little red, a little yellow, a little blue. So the basic idea is some of these are moving away from us, some of them are moving towards us. Now that is not the only reason why some of these stars are different colors. In later chapters, we'll get to why some of those stars are different colors. Depending on the stage of their life or the mass of the stars, they might have different colors. But that's one of the reasons why some of these stars might be different colors, thanks to the Doppler effect. Cool? All right. I think that might be it for light. If not, you'll see another video. So that's that. Of course, ask questions. Always feel free to ask questions. Send me an email. I'm happy to discuss. I will talk to you guys next time. Bye.